Hola! In a previous video, we looked qualitatively at the behavior of light as it passes through a converging lens, like so. Now, we are going to look at a method for determining the distance from the lens and the height of an image produced by a converging lens. We don't need any numbers for this, really. Well, we can use a ruler to measure things like the distance and the height, but we won't be using any formulas. We're not using Snell's Law. That's coming soon. But there are two major tools for determining the nature of an image produced by a lens. Two major tools in this chapter, and those would be the thin lens equation, which I'll look at in the next video, most likely, and ray tracing. So we're going to take a look at ray tracing. There are three so-called principal rays that you can draw in order to locate the image produced by a converging lens. Let's take a look at those three rays. The first thing you'd want to do when drawing a ray diagram is draw your optic or optical axis. That's the line that goes through the very center of your lens. And it's actually not necessary to sketch a lens because we're gonna use just a vertical line to represent the lens. But for now, in addition to the vertical line, I will also draw a thin lens, emphasis on thin. This is a converging lens because it's still thicker in the middle than it is at the edges. And here's a very important observation about these rays. Any ray that comes in parallel to the optical axis, here's the optical axis through the center of the lens, any such ray will be refracted so that it passes through this very special point, the focal point. Now, Snell's law is what determines this angle or the angle of exit over here in terms of the angle of entrance here. That's all calculable using Snell's law. And it really doesn't matter if you go from left to right or from right to left, it's reversible. So if a ray of light were coming from this point, from the focal point, it should be bent so that it exits the lens parallel to the optical axis. It works either way. And that is how we get one of our principal rays. So for now, let's imagine, it's kind of silly. They usually draw something like a tree or just an arrow, but maybe this is a lens like the type of lens you might find in a small refracting telescope, a little bit bigger than the lenses in a pair of spectacles. And maybe a foot in front of that lens or 6 inches, you've got something like a marble or a flower that you're looking at or a bug, something that you'd like to look at up close. Although in this case, well, we're going to see that to magnify something, you have to put it inside the focal point. Right now, I'm going to draw a ray diagram for something outside the focal point. So suppose we were dealing with a lens that had a focal length of, I'll go with 4 centimeters. Because I have a ruler with centimeter markings, and the length of this piece of paper is something like 28 centimeters. So I should be able to draw or fit a ray diagram into the page if it involves distances like this. And you will want to mark the 2 focal points. I think I neglected to mention in the previous video that your thin lens would have 2 focal points, equal distances from the center of the lens. We haven't really proved that, but we can do that later. So from 0 to 4, I'll make a mark here. This is one of the focal points, and then the other one will be over here at 8. Okay, and I will place an object somewhere outside the focal point on the left. Let me pick a definite distance. I'll go with 10 centimeters from the middle of the lens. So let me put a dot here, and I'll do what your book does and just draw an arrow. And your book recommends drawing something that has a height roughly equal to half the radius of your lens, just to assist with visualizing things. I could draw something up here, but of course, if I do that, any parallel rays will look like they're not actually passing through the lens. So once again, I'll pick a definite distance. Go with a 3 centimeter high arrow here. Okay, now, if this is outdoors or in a room illuminated by a lamp, remember, unless this is a light bulb filament at 6,000 degrees Celsius, or a flame, or some other source of light, this thing is reflecting light. And if this was a flower, this point on the flower is reflecting light in all different directions. We could draw a ray in this way, or this direction, this direction, this direction, as many rays as you want emanating from this one single point. But a whole bunch of those rays are going to pass through the lens. Imagine a couple dozen rays going from the tip of the flower through the lens. The lens will, we're going to see that the lenses will, the lens will bend all of those rays so that they converge at some point over here. In other words, the lens will form an image somewhere over here of this object. So you can think of this whole thing as the object. You can also talk about a point on the object, an object point. This object point will have an image point. This object point will have an image point, etc. We could reconstruct an image of this entire thing somewhere over here. And that is the purpose of ray tracing. So here's your first principal ray. Imagine a ray that leaves the tip of this flower and it travels parallel to the optical axis. And we are not going to worry about the fact that the ray would actually undergo two refractions. There's a refraction at each face of the lens. We're not concerned with that because later we'll show that detail can be disregarded when looking at the overall behavior of the lens. So we're going to pretend that refraction only occurs once at the midplane of the lens. That's right here. That's the significance of this vertical line. So you don't even need to draw the lens really, but it helps visualize things. Helps to visualize. And what's going to happen to this ray? Well, you guessed it, because it's coming in parallel, it should refract and pass through the focal point. Again, we haven't proved this. We'll do that shortly, and it is done in your chapter. When you're drawing ray diagrams, the finer your pen point, the more accurate your diagram will be. If you don't use a ruler, you should just drop the class right now because you're a bum. Okay. That's one of three principal rays. What about the other two? Well, I'll get you started here. I'm going to draw a ray from the tip of the arrow through this first focal point. And now it remains to be seen how this ray is going to bend. We know it's going to refract, and we pretend that it only refracts once at the midplane of the lens. And you may have guessed that it's the reverse of this situation. If a ray comes in parallel, it will refract through the focal point. Well, flip this left to right. Imagine a bunch of rays coming in from the right of the lens. A ray like this coming in parallel. What's it going to do when it reaches the lens? It'll bend and pass through the focal point. So we're really just talking about the reverse of that. This ray, which passes through the first focal point, the near focal point, will refract so that it exits parallel to the optical axis. So if you can remember this principal ray, then you can remember this other principal ray. They're the same thing in reverse. And this alone actually is sufficient to determine, it's sufficient to determine the location of the image point corresponding to this object point. Because I mentioned a moment ago that all the rays leaving this point, which pass through this lens, if this lens were behaving ideally, all of those rays would reconverge somewhere over here. We've already located that point. So the rest of this is just confirming that our third ray will just confirm the location of the image point. And the third ray, before we do that, we need to take a step back real quick and apply Snell's law to the refraction of light through a slab of material. So suppose this is a sheet of glass or a thick slab of glass with air on either sides. So the two faces of this glass slab are parallel to each other. And suppose a ray of light strikes the left face of this slab of glass. I will draw the normal at this point. Okay, and hopefully you've had some practice at this point. Is this ray, as it enters the glass, will it refract toward the normal or away from the normal? Well, that depends what this medium is. But let's suppose it's air. As the ray goes from air into glass, it slows down. It will refract towards the normal. Like so. Okay. I will label these angles theta 1. Here's theta 2. And then it's going to refract yet again on the way out. I will draw another normal line. As it goes from glass into air, the light wave should speed up, which means it will refract away from the normal. And I will show in a moment that it's going to bend away from the normal so that, hope this isn't disorienting you, so that it comes out parallel once again to the original incident ray. It's not hard to show that at all. So what's the overall effect of passing this light through a slab of glass? The incoming direction is the same as the outgoing direction. The only thing that's happened is the light got displaced slightly perpendicular. So I tried to draw it so that this angle is equal to this angle. And I'm going to go ahead and call this theta 3, but I know that it has to equal theta 1. Here's why. If I call this N1 and N2, if this material is the same as this material, this would also be N1. Okay, well, let's apply Snell's law twice in succession. If we apply Snell's law to the refraction at the left face, then N1 sine theta 1 has to equal N2 sine theta 2. Fine. But now let's apply Snell's law to the refraction at this face, in which case N2 sine theta 2 must equal N3 sine theta 3. Of course, N3 is the same as N1, so this has to equal N1 sine theta 3. This equality is true. This equality is true. Can't we just skip from left all the way to the right? These two must be equal. So if these two are equal and we divide out the N1, sine of theta 1 equals sine of theta 3, of course, the two angles are equal. I think your book does this problem, and they actually go through all the steps and fail to recognize that you could just skip from left to right. Okay. So the takeaway here is, if you pass light at any angle, because I haven't specified what the angle is, at any angle through a slab of material such that the two faces are parallel, the effect on the light ray is to displace it, but not to deflect it. It's going to come out going the same direction. And that is what we're talking about with the thin lens. Sure, the lens is curved here and here. So this face is not parallel to this face, but you'll notice that at the center of the lens, this face is parallel to this face. So any ray which emanates from this point and passes through or near the center of the lens should be affected in this manner. It'll be displaced slightly, but the direction will be the same. So I could draw that ray coming out, and it would have to be scooted a little bit over, but then it'll come out at the same direction. The emphasis, though, is on thin lens. This is an L. And your book goes through this. They actually look at the geometry, and one of the examples in your chapter 34, they will actually calculate, here's the original, the direction of the original ray. They will calculate the amount by which the ray is displaced laterally, just a little bit of trigonometry. And you can show that the thinner this slab gets, the shorter this displacement gets. So we are imagining a very thin lens, in which case this little displacement would shrink to practically zero. That means our third principal ray can be drawn through the center of the lens, and we'll just pretend as if it suffers no displacement whatsoever. And la-di-da, or ta-da, is that what I meant to say? Ta-da. Nobody says that anymore. It does pass through the same point where the previous two rays converge. That's satisfying. Okay. Now, if I were to draw other rays, some non-special or non-principal rays, we call these the principal rays, could I also get that ray to pass through here? I'm going to say no, because how am I supposed to choose the angle at which some arbitrary ray refracts? There is no rule. The rules only exist for rays that pass through a focal point and emerge parallel, or the opposite, or a ray that passes through the center. We have no way of predicting what those other rays will do. And another remarkable fact is, in a moment, I'm going to measure this distance and compare it to this distance. I'll measure this distance and compare it to this distance. And the relation between all those quantities can be calculated ahead of time using what's called the thin lens equation. That doesn't even require a ray diagram, and yet they're consistent. So it's pretty cool that this diagram will give the same results as the thin lens equation. And your book, just like every other book I've seen appropriate for this class, your book doesn't show why those two should be equivalent. And so one semester I challenged the students to come up with a proof that those two were equivalent, and somebody actually did it. If you're interested, ask me about it. You can prove using geometry that this ray tracing method will give you the same results as the thin lens equation. Okay, so let me go ahead and draw the image now. And I would like to emphasize that all we've really done is show where the image of this point, this object point, appears, and it's right here. But it's fairly obvious that the image of this point would be here. So if the top of the arrow shows up here and the bottom of the arrow shows up here, I think you get the idea. The image of this point would have to be halfway. If this is 1/3 of the way towards the tip of the arrow, its image point would be 1/3 of the way towards the tip of the image arrow. So we have located the image just by looking at the image point corresponding to one object point. Okay, now let's measure some distances here. Usually this will be called y. Y is the object height. Y prime is the image height. If your image is inverted, we consider this to be a negative number. Let me go ahead and write these numbers down. Y is equal to, I've already forgotten what length I chose, 3 centimeters. The image height appears to be 2. All right, that came out nicely. I was expecting some arbitrary decimal, but the image height, I will say, is negative 2 centimeters. And now you might guess the next step. I've already forgotten what my object distance was from the object to the center of the lens. That's 10 centimeters. And that's called S. Let me label that. Anytime you submit a ray diagram, just try to label everything, anything that you think is relevant. Do your best not to clutter the diagram, but things like object and image distances would be important. This is called S. We use the letter S for the object distance, much like the pinhole camera. Remember that? We're using the same notation. So this distance from the lens to the image, that will be S prime. And the more of these you do, the easier it gets. You want to get some practice with ray diagrams, because you will most certainly have a problem on your next exam in which you have to draw a ray diagram and then scan it and email it to me. Okay. What is the object distance? I already said it was 10, right? 10 centimeters. Object distance is 10. Would anybody like to guess what the image distance is? Any takers? I don't see any hands. Well, since the image height was 2/3 of the object height, we might expect the image distance to be 2/3 of the object distance. How do we know that? Similar triangles? Check out this triangle right here. The triangle formed by the object and the central ray. That triangle is similar to this triangle. So we're really just talking about proportions. This compared to this should be the same as this compared to this. And since this is 2/3 of that, we expect this, this to be 2/3 of that. What's 2/3 of 10? 6.666666. You get the picture. Got my fingers crossed. Oh yeah, close enough. I don't know if you can see that, but it's around 6.6. Good enough. S prime, I will call 6.6 centimeters. Now, you may have looked at that and said, well, that looks more like 6.7 or maybe even 6.5. Why is that? The smallest marking on this ruler is 1 millimeter, but guess what? The thickness of my pen line is also about 1 millimeter. So we've introduced some uncertainty by drawing with a finite thickness. That's why I said for more accurate ray diagrams, choose a finer point. Maybe one of those, 0.5 millimeter mechanical pencils. Personally, I detest mechanical pencils. They always break. The lead breaks into little pieces. You drop it on the carpet, you can't find it. You gotta go get replacement lead. For me, it's all about fountain pens. That is where it's at. I'm not using a fountain pen here, but highly recommend fountain pens. They're economical. Okay. Y prime compared to Y should be the same as S prime compared to S. That's the statement I made about proportionality there. There's one thing wrong with this equation. Remember, this number is a negative number. So really the negative of Y prime. The negative of Y prime would be a positive 2 centimeters. If you solve this equation for Y prime, you get Y prime is equal to S prime over S times Y, and then don't forget the minus sign here. You've seen this already. I wrote down the same equation for the pinhole camera. This quantity right here is called the magnification. Magnification. In fact, I think it includes the minus sign. Yes, it does. So in this case, we've got 6.6 over 10, that's 2/3. With the minus sign, the magnification is negative 2/3. And we use the letter M. What does it mean to say that the magnification is 2/3? It means that your image is going to come out 2/3 as tall as your object was. And because it's negative, it'll be flipped. That's all it is. It's very intuitive. So you should memorize that M prime is negative S prime over S. No, I'm sorry, not M prime, just M. That's the so-called lateral magnification. In the next chapter, a different definition will be introduced for the so-called angular magnification. Similar concept, not quite the same formula. Here we're talking about lateral magnification. You're actually taking a distance over a distance, centimeters over centimeters, inches over inches. Okay, light years over light years. Does it make any sense to talk about light years with a lens? Can you make a lens that's 20 light years across? Yeah, you can. Right now we're talking about, this is getting real deep here, unexpectedly, but I'll just make this brief. We are using, what are we using? What's bending the light here? Because this often gets, what is this, the forest? You can't see the forest for the trees. You spend all your time learning these various concepts and rules in the book, and then you forget to take a bird's eye view. Why is the light bending to begin with? What makes the light refract? Go back to one of the first videos from this chapter, before this chapter. You can explain it using interference. You can talk about the fact that this lens is made of atoms. Each of those atoms has electric charge around it, around the nucleus, and that those electrons are made to oscillate by an incoming electromagnetic wave. They then emit their own electromagnetic waves, and those re-emitted waves interfere in such a way that the outgoing ray is refracted. But there's another way to bend light rays. And Newton first pondered this, but he wasn't convinced of the answer. Einstein was the one that gave us a definitive answer. Gravitational fields can bend light rays. So I'm just going to write this down. Some of you are familiar with this. Gravitational lensing. This is something we don't have time to talk about. It's an awesome subject. Extremely massive objects actually do bend light. Even our sun is massive enough to very slightly bend light rays which are passing near it. And I'll save a diagram for another time, but you might think, well, what's more massive than a star? If massive objects are what lens light gravitationally, what's more massive than a star? Well, that would be a whole bunch of stars put together, perhaps, like a galaxy. So if you go on Google and look up images of galaxies doing gravitational lensing, you'll find a lot of stuff. Of course, a black hole can also lens light gravitationally. You may have seen that visualized in, what was that movie, Interstellar? The one where Matt Damon, spoiler alert. Moving on. Okay. Everything I'm presenting here is presented in your book in practically the exact same manner. Let's take another converging lens. I'll even go with the same focal point as I did previously. I was on the other side of the page. Focal length of 4. This time I won't even bother drawing the lens. I'll just use that vertical line to represent the lens. And I'm also going to put the lens off to the side this time because I know where I'm going ahead of time. This vertical line represents the lens. I could draw the lens here, not necessary. 4 centimeters was my focal length. Focal point on one side, focal point on another side. Just to give you some confidence that the two focal points are equidistant. Those of you who may have made wholesome use of a magnifying glass when you were playing with little bugs as a kid, you may recall that it doesn't matter if the sun's coming in and hitting the magnifying this way, you could flip that magnifying glass over. Behavior is the same. Focal points are equidistant. And this time, instead of drawing an object outside the near focal point, I'll put one on the inside. And how about I just put one right at the midpoint between the lens and the near focal point. Okay, so I'm going to draw an object here. And what's an appropriate height? What did I use previously? 3 centimeters? That seems safe. If you choose the wrong object height for a diagram such as this, your rays may go clear off the page, but I think that 3 centimeters will be safe. Okay, so here's my arrow representing my object. This could be a flower. It could be a letter in a book. Perhaps you have trouble reading a book and you need one of those large reading glasses that you hold over the book. Okay. 3 principal rays. One of them comes in parallel to the optical axis and refracts through the far focal point, just like before. Can we locate the image yet? No. This ray has an infinite number of points along it. We need an intersection if we want to figure out where the image is. So we have to draw a second ray now. Let's go with the one that goes through the center of the lens. How does the ray through the center of the lens refract? It doesn't refract. That's the one that we pretend continues along undeflected, or undeflected, unrefracted. Okay, what the heck is going on here? Because these 2 rays don't look like they're going to cross. There is no point over here at which they will intersect. But you'll notice that if you extend these rays backwards, they do intersect. And that tells us that if your eyeball was over here, that's a little weird to think about, but let's say that this is such a small object, it's a very small letter on a page, so that these rays easily fit within your pupil, and both of these rays would then be refracted by your eyeball and meet on your retina somewhere. Looks like I'm making shadow animals over here. That's the only one I know how to do. What is that, an eagle? As far as your eye can tell, these rays really did diverge from a point back here. Let's confirm with the third ray that this really is the location of the image. How do we do that third ray? Well, when the object was outside the near focal point, we drew a ray through that focal point. And as your book points out, if you try to do that here, coronavirus. Not really. If you draw a ray through this point, it's never even going to pass through the lens, so that's no good. What you can do, though, is draw a ray coming out of this, the tip of the arrow, as if it came from the focal point. So it's on a line that passes through the focal point. And what's that ray going to do? Well, if it was coming in from the right, parallel to the axis, it would refract through this focal point. We're talking about the opposite. So it will come out parallel. And I'm realizing I should have been more careful with my diagram, because ideally what's supposed to happen when I extend this ray backwards, this third principal ray, it's supposed to pass through the exact same point at which the other two rays intersect. And it's a little off. They don't all three pass through the same point. Why did that happen? Because I'm just eyeballing things here. I did not actually use a protractor to make sure that this angle was 90. So this ray isn't perfectly parallel to the optical axis. And also my focal point here has a finite thickness. Remember, the thickness of the pen introduces some error. So if you're more careful, you will get a better diagram. What is going on here? Here's the object, but as far as our eye is concerned, all the rays from the tip of the arrow appear to have diverged from back here. And if you repeat this process with rays from this point, the bottom of the arrow, you will find, this is trivial, but the rays appear to be coming from this point. So we've located the image of the tip of the arrow. We've located the image of the bottom of the arrow. Seems fairly clear that the overall image of your arrow is back here. It's taller than the object. Not only that, but it's on the same side as the object, instead of on the other side of the lens as it was previously. So there's a very important distinction between putting your object outside the first focal point versus putting it inside. Now, if you put a little piece of paper here, would you see the image of the arrow on that piece of paper? Now, for this first case, if you've never done this, I highly recommend this. Go to the dollar store with a face mask on, of course, and a big bottle of hand sanitizer. Basically, just wrap your whole body in saran wrap first, and spray everybody with Febreze on your way in, and then go ahead and grab a simple magnifying glass for a couple bucks. $1, it's the dollar store. And stand in a kitchen, some room that has large windows in the middle of the day. Hold up your magnifying glass so that it's between the windows to the kitchen and a refrigerator. And you will see, because the light coming from outside is really, really bright, let's say this is a tree, you will see a nice, sharp, bright image of that tree on your refrigerator upside down. Of course, you don't have to use the fridge. This could just be a white wall within the room. But if you put your magnifying glass at the right distance from the wall, you'll see a nice, bright image. So this image is real. The light rays are actually collecting at this point. You can produce a real image of the object. You could put a piece of photographic film here and take a picture. You will not be able to do that in this scenario because these light rays don't actually converge here. There's no light energy at this point. It looks like it's coming from here, but it's not actually there. So we call that a virtual image. And the image distance, let me go ahead and label those distances now. This is S prime. This image distance is now considered to be negative. Here's a rule that you should just memorize. For a virtual image, we use the convention that the image distance is negative. That's going to make our equations work out later, the thin lens equation. Let me label the object distance, S. Okay, and just like before, this is the object height, Y. This is the image height, Y prime. Let me go ahead and label these things. The object height, what did I go with? It was 3 centimeters, I remember. And the image height, I'll have to measure that. This time it's a positive number. The image is not inverted. So the the image height in this case is a positive number. It's almost exactly 6 centimeters. I'm not surprised. I chose this location for that reason. I remember that that's how it works out. Object distance was 2 centimeters, right? Okay. And you can tell just by looking that the image distance is, be careful, negative 4 centimeters. Let me check. Yeah, as expected. Okay, let's check. Negative S prime over S. Remember, what's this quantity called? This is the magnification times the object height. Well, that would be negative 4 over 2 times the object height was 3 centimeters. Notice I don't actually need units here. It's a ratio of distances. The units would cancel, but I do need units here. 4 over 2, that's 2. 2 times 3 is 6 centimeters. So that's supposed to be the image height. Y prime is supposed to be magnification times Y. Image height is magnification times object height. Don't be thrown off by this minus sign. S prime is also negative, so negative negative gives us a positive. That's why the image height comes out positive. It's upright. A lot of books say erect. They say the image is erect. Your book goes with upright. Okay, so that's formation of an image by a converging lens for 2 scenarios. An object outside the focal length and an object inside the focal length. And it may come as no surprise to you that this use of a converging lens is exactly what people refer to when they say magnifying glass. A magnifying glass is simply a converging lens where you're using it so that the object is inside the focal point. Remember, this was the focal point. Yeah, maybe I forgot to point that out. Do you notice that the image showed up at F? The image is right on top of the focal point. As I recall, that's just something that happens when you put the object halfway from the lens to the focal point. I'm not going to do this diagram, but I encourage you to get at least an 8.5 by 11 sheet of paper, maybe a larger piece of paper if you can get your hands on one, and repeat this again, but put the object closer to the focal point, maybe 3/4 of the way from the lens to the focal point, or even right on top of the focal point, and see what you can determine. There's something interesting about where the image shows up, and we will look at this in the next chapter, but try a ray diagram where your object is near the focal point, and you could put it on either side. But in each case, if it's near the focal point, you'll see something interesting. Before doing a similar ray tracing diagram for a diverging lens, I would just like to point out or summarize, if you've got a converging lens and you put the object outside the focal point, you will get a real image on the other side of the lens, and that real image will be inverted and generally reduced in size. I don't think the reduction in size is always the case. Sometimes I think you will get a larger image, but it should be inverted. That's just a feature of the converging lens. If you put the object inside the focal point, you will get an image on the same side of the lens as the object, and that image will be enlarged. And I think it's upright, and I think it's almost always enlarged. Don't quote me on that. Okay, let's look now at a ray diagram for a diverging lens. And because we haven't done this yet, I'll go ahead and make a silly sketch of the lens. And with the benefit of hindsight, or is it foresight for me? I'm also going to put the lens off to the right. Okay, so we don't really need to draw the lens, but maybe it looks something like this. Thinner in the middle than it is at the edges. But we're not actually going to draw two refractions. We just pretend that all the refraction happens at this vertical line, the midplane of the lens. Okay, I have to choose a focal point. Let's go with exactly what I did previously. I'm going to extend this just a little bit so I have room to draw the second focal point. I will go with 4 centimeters on either side. You know what, let me use the space that I have available, 6 centimeters. Let's suppose this diverging lens has a focal length of 6 centimeters. Well, I should point out right now, the focal length for a diverging lens is considered to be negative. F is negative. That might seem a little improper to say that a length is negative because we normally think of length as a positive number, but just be flexible. Go with it. Okay, focal point, focal point. As I recall, for a diverging lens, it really doesn't matter whether you put the object here outside the focal point or here. In both cases, you're going to get a virtual image, which will be on the same side as the object, and it will be upright. Let's confirm at least half of that statement. I'll pick a reasonable distance. How about 10 centimeters again for my object distance? Okay, so S will be 10, and for my object height, well, if I draw it too tall, it seems unreasonable that the rays coming out parallel would actually go through the lens. So I'll go with 5 centimeters for the height. All right, object distance is 10. Object height is 5. Focal length is -6. How do we draw the 3 principal rays? Or are there 3 principal rays? This is a diverging lens. Maybe things are different. Okay, well, I'm just going to blindly start by drawing a parallel line. Yeah, and you can already see that I didn't make my lens sketch tall enough. If this was the actual lens, this parallel ray would go right past it. Look at that, easy fix. Okay. Voila. Ta-da, la-di-da, whatever. Is this ray going to refract through the focal point? That's not what a diverging lens does. A diverging lens takes parallel rays and spreads them out, hence the name diverging. Hopefully you've read the book and you know the answer, but this ray, which comes in parallel to the optical axis, it is going to diverge as if it came from the near focal point. So you take your ruler and you make sure that the ruler passes through the point where it strikes the lens or the vertical line, and that it goes through this near focal point. So the ray gets refracted out like this. Before I draw the backwards portion, let's get the other 3 rays. Well, one of them is easy. Just like before, at the center of the lens, the 2 faces are practically parallel, or they are parallel. And so this ray will be undeviated. It just goes right through it. That was easy. And just like the case of a converging lens with the object inside the focal point, these 2 refracted rays are not going to converge over here. There will be no real image formation on the other side of the lens, but you can already see that if you extend this backwards, these 2 would intersect. How do we do the 3rd ray? This is the tricky one. The 3rd ray for a diverging lens, I could pause and cheat, like think about it for a second and come back. It's obviously going to involve this this other focal point. So how about I just go ahead and draw a ray through that focal point. You know what? We already used that focal point, right? We used it for this ray. Ah, I remember. As many times as I've done this, I still tend to forget this if it's been a while. Here's what you do. You draw a ray on its way to the far focal point. Can I get that in the frame all at the same time? Here's the object point, the top of the arrow, or the tip of the arrow, and I'm going to aim for that far focal point. Got the ruler going through both. Of course, once the ray gets to the vertical line, which represents the lens, it's going to refract, and we know that it's not going to bend down. This is a diverging lens, so it should be spread out, so to speak. And it's really just the opposite of this ray. I think you see that this is going to exit parallel to the optical axis. That's the tricky one to remember. Unless you practice, and then nothing's tricky, right? Okay, are those two opposite? Is there a way of thinking about that? Yeah. Imagine coming in from this direction. This ray would diverge as if it had come from this focal point. That's the exact opposite of what we did here. Okay, so it's really just one idea in reverse. How about that? Arguably, you just have to remember two principal rays because these two are mirror images of each other in some way. Here's the part where we can extend each of these backwards. This ray appears to be coming from this direction. This ray, which comes out parallel, looks like it came from this direction. And we don't even need to draw anything else for this ray. We've already got the solid line. So I see that all three rays appear to be diverging from here. This must be the image. So like I suggested, your image is virtual because remember, these rays are not actually coming from this point. They only appear to be coming from this point as seen by somebody over here. You cannot, if this was the surface of your refrigerator or the white paint on a wall or a piece of photographic film, you won't see an image there. It's not a real image, it's a virtual image, but it is upright. And what can we say about this number? The image, distance S prime. I think it's considered a negative number, even for a diverging lens. There's a table in your book which lists all of the sign conventions for ray tracing and the thin lens equation. So you'll want to memorize that table. But if you get practice with the homework problems, you will know those rules anyway. Maybe squeeze that onto your note card. Note cards, well, that'll be different for an exam which we take remotely. More to be said about that later. Let's check all the distances here. The image distance. Okay, it's not a nice integer this time, unfortunately. To me, it looks like it's 3.6, something in the vicinity of 3.6. Okay. Y prime looks like 3.6. And it's upright. I believe it gets the plus sign. What about, wait, I'm sorry, not Y prime, that's S prime. S prime, that's still considered negative 3.6 centimeters. Yeah, I was measuring the distance of the image from the mid plane of the lens, that vertical line. And then Y prime, that's the image height. I'm gonna go with 1.8 or 1.9 centimeters. I'll say 1.8. You know what? That sounds about right because using 3.6 double 1.8, 10 is double 5. Okay, let's check. Y prime should be the magnification, the lateral magnification M times Y. Well, that would give us negative 3.6. I goofed again, negative 1.8. The image distance is negative 1.8. Now, what's going on here? I've totally confused myself here. Did I write these distances correctly? 10, 5. This is the object, is it not? Okay. Let me try this one more time. I prime should be negative. What is the image distance? It's that 3.6 compared to, yeah, so I think I was misled when I was looking at the ratios just now. Negative 3.6. And there's a minus sign in front of this whole thing, over the object distance of 10, okay, times the object height, which was 5. Okay, image distance over object distance with a minus sign times object height. 3.6 divided by 10 times 5. So yeah, positive 1.8. Yeah, this did work out because 5 over 10, there's your factor of 1/2. Multiply that by the 3.6. All right. So this relation here, which I've crossed out, appears to work for a diverging lens and a converging lens. I'll leave it to you to do another ray diagram where you put the object inside the focal point of this diverging lens, and you should still find that you get a virtual image on the same side of the same side of the lens as the object, and that virtual image will still be upright. Yeah, that's the last scenario that you can check. And I mentioned a couple times the fact that if you're nearsighted, your spectacles, your third and fourth eyeballs, well, they're diverging lenses. So if you're looking at something, if your eyeball is here, pupil, here's the lens in front of your eyeball mounted in the glasses frames, and you're looking at something over here, maybe this, let's see, nearsighted. Nearsighted means you're good at seeing things that are near. You're not so good at seeing things that are far. I remember the day that I suspected I was nearsighted. I was in 3rd grade looking out the classroom window while Miss Heath was, I forget what she was lecturing about, but elementary school teachers, they don't lecture. You know what I mean? I realized I could no longer distinguish the leaves from each other on the tree outside. I knew that I used to be able to do that and I couldn't anymore. And so I suspected that I was nearsighted. So if this was a leaf on a tree, too far away for me to see sharply, when those rays pass through the lens of my glasses, the image that's formed is much closer to the lens than the actual object. Well, maybe this is close enough for my eye to actually see. That is what a diverging lens does for a nearsighted person. It takes the object that you're looking at and replaces it with an image that's near enough to your eyeball so that your eyeball can focus it. All right. In the next couple videos, we'll go back to using actual math. This is 3C after all. You would learn these ray diagrams even in a non-calculus based class that covers optics. We'll use math to show that, well, first of all, we'll just look at a single spherical boundary between air and glass, for instance. Then we'll stack up 2 spherical boundaries. That's a lens. And we'll show that this thing really does converge light rays in a manner consistent with these ray diagrams. That'll be called the thin lens equation. So the thin lens equation and ray diagrams, they give the same results. You want to know how to do both.